The last part of chapter one deals with Earth's grid system. It's how we navigate across the planet, and it is absolutely essential for geography because geography is, after all, a spatial science, and we can't study the space around us if we don't have a measured and organized system by which to coordinate different locations around the planet. And so the grid system that we use consists most commonly of latitude and longitude. It creates um, a net-like pattern across the Earth. And we'll talk about latitude and longitude in just a second. We'll also touch on great circles and small circles. What exactly is their importance? We'll talk a little bit about time zones and how that relates to longitude in this case. And then we'll talk about some mapping specifics. So to start, trying to advance the slide. Hello. Okay. Um, to start, we're looking at latitude lines. And latitude lines are all parallel to each other. It's why latitude lines are also called parallels. We label the lines starting at 0, which is the equator. The equator is a latitude line. And so we start at 0 and we are either heading north up to the North Pole, which is 90 degrees. That's the latitude, quote unquote, line at the North Pole, 90 degrees, but we're increasing from 0 to 10, 20, 30, 40, etc. as we go north, all the way up to 90, and 90 is the max. Or we can head south, and we get the same thing. We're increasing to the south, 10, 20, 30, 40, 50, etc., till we get to the South Pole, and that's 90 degrees south. So it is important to use these degrees north or degrees south so that we know which hemisphere we're in. The northern hemisphere, the equator splits the Earth in half into the northern hemisphere and the southern hemisphere. And that's why we use degrees north or degrees south. Some other information about latitude lines is that they are not all the same length. The equator is the longest latitude line, traveling around the whole middle of the Earth, and the lines get shorter and shorter as we get closer to the poles. We will also talk about great circles. The equator happens to be one, but we'll come back and define that later. Any of the other latitude lines are considered small circles. But again, come back and define that in a minute. So those are latitude lines. They also run east and west. So if I'm walking along a latitude line, I am walking either to the east or to the west. For me, when I was first trying to memorize latitude and longitude and keep the two straight, keep them separate from each other, I always thought of latitude lines as like rungs of a ladder, right? Like if you're climbing up a ladder, these are the things you step on. Um, so I know ladder is spelled with, you know, two D's, but kind of sound alike, and that was enough for me. So latitude lines are like rungs of a ladder running parallel to each other. Longitude lines, on the other hand, they all intersect each other. They intersect at the North Pole and at the South Pole. Um, they are all the same length since they're all passing through the same 2 points. The prime meridian is the 0 degree line for longitude lines. And the prime meridian runs through Greenwich, England. That's right here, Greenwich, England. That is how you pronounce that word, Greenwich. The prime meridian is the reason why longitude lines are also called meridians. Um, all the lines are equidistant from each other, all the same length, as I said before. They are labeled from 0 to 180. And that is because we have the prime meridian is 0, and we count upward as we go to the east or to the west from 0. So we're going up 10, 20, 30, 40, da, 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 all the way around to the opposite side of the earth. Again, if I'm going east or west, we end up, boom, all the way at the opposite end of the opposite side of the earth. And if you remember a bit of your geography, a circle, we're dealing with a sphere here, but a circle has 360 degrees. And so what's half, and that would be fully going around the Earth, 360 degrees. So what's half of that? 180. And so heading around to the other side of the Earth, going eastward or going westward, we end up at 180, all the way on the other side. So that's why longitude lines are all labeled 0 to 180, and we use degrees east or degrees west to indicate which hemisphere we're in, right? Being split by the 0 degree and 180 line. The international date line is the other name for that one. But it's splitting the Earth in half, just in a different way. And so east of the prime meridian or west of the prime meridian, those are the two hemispheres, and why we use degrees east or west. All of the longitude lines are also great circles. And so I'm going to get into that definition now. What does that mean? So, great circles are any plane. We're looking at this right here. Great circles are any plane where you can slice the Earth in half, and that slice passes through the center point of the Earth. So any line that I can draw wrapping around the Earth, and if that slices the Earth in half through the middle, that is considered a great circle. The small circle, on the other hand, is any other line that I can draw that wraps around the Earth, um, that is not cutting the Earth in half, not passing through its middle. So when I said the equator is a great circle, that's because if I were to cut the Earth in half right along the equator, Imagine I'm cutting a big cake. I don't know why cake came to mind, but imagine I'm cutting a big cake and I follow uh, the the line that the equator delineates, and I am truly cutting it in half. I'm going through the middle, cutting it in half. All of the longitude lines, if I go back uh, here, all of these longitude lines, if I were to cut along any one of those lines, I would be cutting the Earth in half through the center. So those are the great circles, the small circles, again, other than the equator, any of the other latitude lines, that would be those would be small circles, not cutting in half, not going through the middle. And again, any other diagonal or any direction, as long as it doesn't pass through the equator, it is a small circle. So why does this matter? Who cares? Um, let me. hmm, Well, no, let's do this. We'll come back and talk about why this matters in a minute. So just keep that in the back of your mind. First, I just wanted to talk real briefly about time zones and how our time zones are based on our longitude lines. The prime meridian is shown here on this map, again, passing through Greenwich, England. Um, and what we have basically are uh, a certain width, a certain width of land along these longitude lines that constitute a time zone. That's the basis for the time zones anyway. It's a certain width of land. Now, of course, with the different countries and states, these political boundaries make it a little more complicated. So, of course, we do have zigzagging, just so that we're not, cutting too many countries in half or uh, too many states in half. But in some cases, it becomes unreasonable to not split countries or states in half. The US and Canada. The US, we have multiple time zones. So does Canada. So does Russia. So does Australia. Australia even does like a 30-minute time zone. Uh, I don't know why. But so does India, and Nepal and some other places have what are it's called non-standard time. But in any case, that is why these time zones make stripes, but zigzaggy stripes, because they are based on longitude, which comes up and down. Um, that's a little bit of what I wanted to say about time zones. The reason that the time changes the way that it does. Right? Like it could be 2 p.m. in Eastern time, 1 p.m. in Central, noon in Mountain, Pacific time, etc. The reason that happens is because the direction of Earth's rotation, which is counterclockwise. Earth is rotating in this direction. We're all moving that way. Okay. In any case, Um, moving on from the grid system itself, there are some important aspects to maps. That's part of geography also. So we'll talk about maps themselves, the scale that is on a map, and different map projections. and why these things are important to not just understand, but to use. So the map, um, the 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 basic definition of a map is that it is a certain area. It's the view of the area. They're typically bird's eye view, right? Seen as above, and they are a shrunken representation of that land, right? We were just looking at a world map, and it fits on a screen. The world is obviously much bigger than that, but we shrink things down so that we can fit them. We can fit them on maps. And so the scale then is important to recognize because it is the ratio of the distance on the map, like taking 1 inch on a map, and then comparing that to what is that distance in the real world, in real life. So there's a few different ways that we can represent scales. The first one is one of the easier uh, scales to use, bar scale or a graphic scale, it's called. It's these little doohickeys that you might see on a map, and they are literally showing you a distance, whatever distance that might measure on a ruler, like maybe a centimeter. I mean, it depends on what screen size you're looking at, but say that's a centimeter. That's maybe 2 centimeters. Well, it's telling you how far that is in real life, 100 meters. I can measure the 2 centimeters on a map, but in the real world, that would be 100 meters. Or same thing here. Maybe that's about an inch if I'm measuring that with a ruler. But if I take the ruler to a map, or this map specifically, I would be looking at 330 feet. So that's where a bar scale can just kind of be a bit easier to read. Um, the representative scale or representative fraction, this is a maybe a little trickier for some folks to wrap their head around because there is no unit here, unlike the bar scale or the verbal scale. There's nothing telling me, feet, meters, inches, what. But the way that we read this is that it's still a ratio, but it's unitless. It means I can use any unit. And the ratio of the units is that 1 unit on the map equals 10,000 units in real life. And if I can pick any unit, I'm going to pick inches. It means 1 inch on the map equals 10,000 inches in real life. You have to use the same unit on both sides. That's the trick with the representative scale. I could say 1 centimeter on the map equals 10,000 centimeters in real life. I could do that too. Of course, 10,000 centimeters doesn't really mean a lot to me. Um, I don't really have a sense of how long that is. How far is 10,000 centimeters? So, what I'm probably going to do is um, convert centimeters into meters or even kilometers. It means I need to know how many centimeters are in a meter, and I need to know how many meters are in a kilometer. Or I could just plug it into Google and it'll just tell me. How many kilometers is 10,000 centimeters? But that's where this representative that's what the representative scale means. Um, but it is a scale nonetheless. And the third one, verbal scale, this one is fairly easy to use as well, I think, because again, it's telling you a unit and what unit this is on a map. I measure 1 centimeter on a map, and that would be 100 meters in real life, or 1 inch equals 833 feet in real life. So again, using a ruler, I can measure distances pretty easily on maps. Uh, and it gives us a sense of how, um, what kind of distances are we looking at on these maps with different scales. However, on this slide, all of the scales that I've listed and drawn here, they're actually all the same. So they all represent the same thing. Here, 1 centimeter equals 100 meters. That's 10,000 centimeters, 100 meters. Um, or 1 inch. 1 inch equals 10,000 inches, which is about 833 feet. Okay. Something else about our maps. We can obviously show, I'm going to say different sized maps. But what it really is we're looking at different levels of detail um, in these two maps in particular. And it's a little counterintuitive to say that, okay, a small scale map, we see a larger area. And the numbers here for the scales are huge. So why do we call it a small scale map? Because it shows a small amount of detail. The map to the right, um, you know, try to point out where you live. I mean, we could sort of pick out Memphis, the bottom right corner of, or bottom left corner of Tennessee, um, southwest corner of Tennessee, but that's about it. I'm just sort of estimating where Memphis is. I don't see a lot of detail here, just, I can see the states. But that's about it. The large scale maps show a large amount of detail. So this here, I'm looking at a large scale map. I can see a lot of detail. I can pick out where Memphis is, or the University of Memphis, rather. I might be able to estimate a little bit where I live. Um, but it is showing a smaller area than a world map or a map of North America here. The numbers for the scales are smaller. Instead of 1 inch equals 1,500 miles. Now, with the large scale map, we're looking at 1 inch equals about 1.5 miles. So, to keep it straight, remember that small scale and large scale maps are describing how much detail is being shown. Small scale maps show small amount of detail, large scale maps show a large amount of detail. So that's an observation that can be made anytime you look at a map. Um, are you looking at a small scale map or a large scale map? How does that affect what you can see or what you can't see? Those are all things to keep in mind. And then we have map projections. A map projection is an important thing to keep in mind because any map, especially world maps, that we are trying to make, there has to be some distortion occurring because the world, the Earth, a globe, is three-dimensional. It is a sphere, it's a three-dimensional sphere. And we're trying to make maps that lay out flat on a sheet of paper or digitally on a sheet of paper, quote unquote. So none of those two-dimensional maps or paper maps can perfectly represent the three-dimensional nature of Earth. It can't be done. And so we have different types of projections where we take the Earth and we are projecting, or if you want to think of it this way, stretching out certain parts of the Earth to fit onto the paper map. Or in other cases, we might be kind of squashing other areas to fit them onto the map. And so each one of these projections produces a very different type of map. A cylindrical projection produces what's called the Mercator map, a Mercator projection. Planar projection. We're projecting part of Earth onto a flat sheet of paper, like at the North Pole. So we get the North Pole in the center and a very strange kind of distortion along the outer edge of this mnemonic projection. Conic projection, making a cone, um, wrapping it around the Earth this way, and then unfolding it. Oval projection, uh, again, areas in this case at the poles are kind of squished. And then we have some projection or some stretching out at the equator in certain spots. So, right, none of these show perfect representation of the sphere of Earth, but some are better than others. Some have less um, distortion than others. Some maps preserve area better. Other maps preserve um, distance better. And of course, um, you know, if you're going to be working at the North Pole, you want a map that shows the North Pole. You wouldn't want to use the Mercator projection, which just sort of cuts off most of the North Pole. So that wouldn't be very helpful. Neither would the oval projection or the conic projection. Those wouldn't be very helpful if you wanted to work um, at the North Pole. So those are all considerations that geographers need to consider when making maps. Um, what kind of map they want to use, what's their base map going to be, um, all kinds of things like that. Um, an example that I like to give with distortion is looking at the Mercator projection map and seeing just how huge, first of all, Antarctica is, and also Greenland. At the poles, they are very stretched out. I'm trying to bring up Google Earth. So, here we have a Google Earth program that I love, and uh, it is an accurate representation of the Earth because it's three-dimensional. Its interactivity makes it three-dimensional. So, um, that's not what I want. Don't read my email. Uh, what am I looking for? Mercator projection. And this one's pretty good. Um, so what we're looking at is a Mercator projection map. This is Greenland, and I like to compare it to South America or Africa, like based on their sizes, which is bigger. Greenland looks bigger than South America, maybe about the size of Africa. That's in this Mercator projection. Also, this huge mass down here is Antarctica, looking gigantic. But if we look at the globe, and I can even measure the size of these continents. Oops. So from the north to the south tip of Greenland here, about 1,600 miles. 1,600 miles. Gonna come down here and look at South America. Remember, Greenland was looking bigger than South America on the Mercator projection map. Well, South America is 4.5 hundred miles, 4,500 miles from north to south. Obviously, it is much larger than Greenland. The same thing with Africa to an even larger extent, going from north to south, almost 5,000 miles in that rough estimate. So there is clearly a lot of distortion in that Mercator projection map, just to bring that up once more, right? Greenland is not that big. It is not bigger than South America or Africa. So this is the distortion that we can see in uh, certain types of projections. Um, Back to the different projections and great circles. Um, there's an interesting thing that happens with different types of projections and related to great circles. These mnemonic projections um, show us great circles as straight lines. That's just the way that the area is being preserved and or distorted in this projection. Uh, in this case, we're looking at um, on one end of the line, we have San Francisco. On the other end of the line, we have London. Now, the Great Circle appears straight in this projection, the rum line, is curved. Notice on the Mercator projection, though, we have the opposite, where this room line is now straight and the great circle line is curved. So I want to ask you, which line is the shortest distance from San Francisco to London in real life? In other words, if you get on a plane in San Francisco, go to London, what path is your plane going to take? It is going to take the shortest distance, saving fuel and all. But which path is it going to take? A great circle path and fly over Greenland? See, it's passing over Greenland in both projections. Or is it going to follow this room line and stay mostly over the US, passing over a pretty good section of the Atlantic Ocean? Which one is actually shorter in real life? Well, I'm going to bring up Google Earth again, kind of popping in and out of here. Um, we can recreate that in Google Earth because if I start at San Francisco, I'm going to use my little ruler tool again. We don't really care about the distance so much when I'm drawing this line, because when I draw this line, this is going to be the shortest distance from San Francisco to London. And San Francisco's right about there. As I'm coming over the globe, notice how that line curves, or it looks like it's curving, kind of overshot, but so where is this line going? We're passing over Greenland. The shortest distance between these 2 points is not that room line. That's just the Mercator projection making it look like that. I also like to show folks, I once flew from Houston or Dallas, doesn't matter, to Japan. And it was really cool for me because we did not fly out to Hawaii. Again, that's what the Mercator projection would make us think is the shorter distance. But if I'm actually pulling this line over to Japan, the shortest distance comes way up here close to Alaska. My flight actually did pass close to Alaska. They try to stay near the coast just in case there's emergencies. You don't want to be in the middle of the freaking ocean on a 17-hour, well, that would be like a 24-hour flight or something. So they stay near the coast. But it's not what you would expect because when we think of the map, we think of the Mercator projection, just like straight shot, US, Hawaii, Asia, but the Great Circle Path, that's what this is. If I continued to draw this line to end up back where I started over here, I'm not going to do it. But if I did, it would be a great circle, and I would be able to cut the Earth in half along this line, going all the way around the Earth. That's a great circle path. So that's why I brought up great circles earlier, um, because they actually uh, are meaningful when we're looking at traveling long distances. They are used not just by airlines, commercial and uh, private, um, but by ships. Ships crossing the oceans, they use great circle paths as well. So the answer to this question, which line is the shortest distance? It is the Great Circle Path. Even though it looks longer in the Mercator projection, that is just due to the distortion happening, especially uh, up in the northern polar regions. Okay, so our very last section here, uh, not too long. I just want to touch on remote sensing because we did bring it up earlier in the chapter as a way of gathering data. And that's really important in geography to be able to collect your data. And remote sensing is even better because it means that you don't have to go to a physical location to collect the data. There are certain types of instruments, there's certain types of data, satellites. We can collect a lot of information using instruments like this, and we don't have to go there. And so I've listed a variety of types of information that we can collect using remote sensing. Um, I'm not going to read them out for you, but um, instead, I want to talk about two types of remote sensing. And one of those types is active remote sensing, the other is passive remote sensing. And sorry, active remote sensing involves sending out some sort of signal from the instrument, and that signal comes back and gives you the data. So there's an active signal being sent out. Sonar is an example. Sonar is emitting sound waves. Those sound waves go out, they bounce off whatever object is in their path, and the sound waves come back, and we can measure the distance uh, of that object from our sonar. Um, this is how um, wartime ships were looking for U-boats, right? U-boats, German subs. They use sonar, and when they got a ping, it was, a U-boat in the vicinity. They could also measure the depth of the ocean and collected a lot of ocean depth data. Just the sonar was going down and pinging off the bottom of the ocean floor, so we could measure the depth of the ocean that way. Infrared, infrared goggles, or what have you. That's also active remote sensing. We are using infrared light um, instead of um, visible light. I mean, they're used in low light situations. Um, so infrared is another type of signal or radiation. Passive remote sensing, on the other hand, is an example here is a camera. Our cameras do not send out any signal when we take a picture. They just open a shutter, collect whatever light is coming at them, close the shutter, and you get that image. So it's passive because it's not actively sending out any signals. Hmm. Our eyeballs are also passive remote sensors. I guess they're not very remote, but they are passive sensors in the sense that, we don't have X-ray vision. We are only, well, I guess X-rays wouldn't be active either. We don't have laser eyes. Yeah, we are just collecting the visible light that's coming to our eyeballs. Different types of remote sensing can be used depending on what data you want to collect. GIS here is a part of remote sensing. GIS stands for Geographic Information Systems, and I'm going to tell you that there's a question on the first exam that asks you what GIS stands for. So, boom, memorize it. Geographic Information Systems. I think that's important to know because it's such a big part of geography, um, and it's a big part of a lot of jobs that are out there. If you get a chance to get a GIS certification, which the Earth Science Department offers, it can be a really useful addition to a resume, depending exactly on what you might be doing. But there are definitely jobs out there that just focus on GIS. So, what GIS is, we are looking at our spatial data, we're looking at our maps, whatever area we're interested in, we're taking that and some other attribute data. So it was just some other data, and we're putting it on a map. I know people who work for the city with GIS, and they are uh, updating like property information on on the maps, like just house by house, street by street. Um, and so the attribute data there is uh, property plots, making sure that numbers match. It's for like the post office, making sure the house numbers match certain things. Da, da, da. But yeah, it's going over an area and looking at whatever attribute data you want to look at. I've talked about political data before. Who's voting in what way in the counties or in the neighborhoods, or or by state. Um, that would all be related to GIS. GPS, on the other hand, is an instrument that uses GIS. It is using the spatial data, um, and it's usually used for traveling. GPS is Global Positioning System, and so it can give you your location globally, ideally. So GPS is a part of GIS, and as I said before, one that we use uh, anytime that we open up our phone and are looking for directions. Um, I use it a lot. Um, Trying to find, a gas station, or what's the closest grocery store, stuff, boring stuff like that. Um, so that's all GPS. And one thing about geography and GIS is that our maps can contain multiple layers of data. So it doesn't just have to be a map with West Nile virus outbreaks. It doesn't have to be just that. We might look at West Nile virus outbreaks and the amount of rainfall that an area's received, or the type of vegetation uh, in those areas. Because, where do mosquitoes live? Not everywhere. So we might want to see if vegetation plays a part in something. Those are physical features. You can add cultural features as well. But all of this to say that we can put together a composite map with many of those layers on top of each other. I also wanted to just kind of again plug Google Earth because I do love it so much. And we can get there's certain data that we can obtain from Google Earth. It's free. You can download the software, or you can download the app. You can go to the website earth.google.com, and the program, the software, in any case, I mean, you can go anywhere in the world, but not just Earth. Um, some years ago, popping out of that again. Some years ago, they added that you can check out the sky. The sky is pretty cool. Like you can be looking at galaxies, certain galaxies. Oops. And all these stars they have labeled. I think I lost Andromeda. Anyway, there's other galaxies here. So I don't know if you like your stars and things, you can geek out over that. I uh I really thought it was cool when they put out the moon. So there are certain areas that have higher resolution pictures than others. So trying to zoom in here. So these craters have pretty nice um resolution, and the three-dimensionality here isn't all that impressive. But I like super geeked out over Mars. When I saw that they added Mars, I wasted a whole day. Well, I don't think it was a waste, but I spent, I think, a whole day uh just looking everywhere around Mars, seeing what I could see. Um, and so again, there are certain areas that have higher resolution than others. I'm trying to find some of the mountains. I don't know. But in any case, just while we're looking at this here, this is a pretty classic river valley. The pattern of that. So it's just really cool to be able to come in here. Oh no, I'm sorry, those are sand dunes. My bad. Um, but we've got some elevation relief. There's some little mountains that were probably, or maybe they're sand dunes too. I can't tell. Could have also been volcanoes. Um, no, wait, I take it back. I those are river valleys. Uh, coalescing into a larger river valley. So I don't know. I could spend more days wasting on Mars, but I thought that was really cool. Oh, and they also have in some places historical photos, which is super cool for Memphis. Go back to Earth. So these are going to be um uh well, there's a couple ways of looking at some historical photos. One is with the aerial photos. Don't need all those roads. Um, actually, let's go to, I don't know, Overton Park, and I'm gonna use this little icon here. So this is a recent photo from January of this year, but I can go back to 1997, or this one's 1985. Oh, that is one issue with some of the historic photos. They're uh very poor resolution. Um, but if I zoom out, I can see um some things like I'm thinking Collierville is not looking as populated as it is today, or Lakes of Forest Hill. There's no houses there, but then they're starting to build some neighborhoods. So there's some things to check out, like if you wanted to look at where your house is, see how that might have changed, or I'm trying to find the University of Memphis now. Where am I? There we go. So the University of Memphis in 1998. We've got some of the main buildings here. Um, but the uh, Living Learning Residence Complex is different. Um, yeah, there's a lot of differences to look at for these historical photos. You can see how things change over the years. There's the newer configuration of the resident complex. Oh yeah, the parking lot across the tracks. We had the printing services building where the rec center used to be. Okay, anyway, sorry. Um, I find that stuff pretty fascinating. To finish up though, we want to finish up here. Um, Yeah, it's fine. There's some other remote sensing techniques. LiDAR. LiDAR is a fairly new way of collecting high resolution elevation data. So we can collect elevation data using satellites, but LiDAR is more of a targeted approach. This is active remote sensing because LiDAR is using light, certain type of light, that can penetrate vegetation. And so we don't have to worry about getting signals bouncing off of trees or houses. Um, LiDAR kind of cuts through that, goes through dense vegetation. And so we get actual ground relief in places where we maybe were never able to before. And this picture on the right is showing really, really nice detailed elevation data for some volcanoes out west. On the west coast, we've got Oregon, uh, maybe Washington. I don't recall exactly. But there's Mount St. Helens, Mount Adams, and Mount Hood way in the distance. Volcanoes. So we're developing new technology all the time. And again, to create composite maps, we can collect a variety of data. There's different information that is being listed here, topography, uh, property parcels, different zoning, floodplains, wetlands, different land covers, um, like brush versus plains versus rock, land cover, forest, soils maps. We can put those all together to make one composite map. And so there's a couple different maps on the right here that show different data sets. The land cover map for all of Washington State, all those different colors represent different uh, types of land. And we've got the cities and the counties also on that map. Here's the West Nile virus map I've mentioned a couple times. It's just a really powerful tool, geography, a way of visually representing this data. So, in summary of chapter one, we know now that geography is a tool that helps us to understand the natural and environmental environments around us. Spatial interrelationships is a really important part of using geography. That's kind of usually our main goal, trying to understand the spatial relationships between different attributes. We learned that data can be collected directly or remotely. We can go to locations and collect data, but we don't necessarily have to. We have remote sensing technology. We learned about systems, different Earth systems or subsystems. We learned about interactions between inputs and outputs, how that contributes to either positive or negative feedback loops, and that going forward, we will be learning about interactions between the lithosphere and the hydrosphere, mainly. Earth's landforms, a lot of them are made through weathering and erosion of the solid part of Earth, but through water. Um, not all of it, but a lot of what we'll talk about involves water in some capacity, uh, altering the solid part of Earth. So that's what we have to look forward to the rest with the rest of the class. And that is the end of chapter one. So make sure that you uh, do complete quiz one. We've got quiz one that's going to be coming up and due since we have finished chapter one now. All right. So I hope if anybody has any questions, just let me know.